Okay. Yeah, thanks. Thank you very much for the introduction. And this is the last day of our workshop, and I'm happy to see that there are still quite a number of visitors here. So as a local person, I wish you a pleasant journey back home. And today I'm just going to talk about a very simple numerical method for the non-cutoff Boltzmann equation. Okay, this is a very brief introduction of the background. I think it's not very unfamiliar to most of you that Boltzmann equation is a fundamental equation of the gas kinetic theory. But I also see a lot of students over here, so I use this page to introduce a little bit about the background of this equation. So first, this equation is to solve fluids, okay? And usually when we solve fluids, we consider the fluids as something like this, which means that you have the continuum hypothesis. You just pick any point in the space, and there's always some gas there. But actually, you know, this is not true. You can pick a very small cube from this big cube, and then magnify this. You can see that what's inside this cube is actually a lot of molecules flying here and there. So this is what this picture means. And from this picture, you can see that you can find a lot of spatial points where there are no gas, no particles over there. So based on the continuum hypothesis, we can get Euler's equations, Navier-Stokes equations. But if you look at this picture, then this continuum hypothesis is no longer true. So you want to use another way to describe the fluids, and this is the gas kinetic theory. So it uses a statistical way to describe the state of fluids. So mathematically, the function is called a distribution function. It has three variables. The first one is time, because we want to solve an evolution problem. And the second one is space, x. This is also easy to understand. And we have another variable, which is v. And this v is the velocity of the gas molecules. Then what does this distribution function mean? If you multiply this function by a microelement in space and multiply the result by, again, a microelement in the velocity space, what you get is a number of particles with position in this small element and velocity also in this small element. So this is the meaning of this distribution function. So in general, it's like a probability density function. It's like that the probability of a particle appearing at point x and flying with speed v. So this is the idea of this distribution function. Okay, now we want to simulate the dynamics of this distribution function. How can we do this? We just consider two effects. The first one is the transport. This is just a linear transport. Okay, I have a particle, its velocity is v, it moves with velocity v, so I get this convection term. And I have another thing, which is a binary collision. It means that gas molecules interact with each other. So you get this term, QFF. We call this term a collision term. And here we only consider binary collision. It means that we only consider the case when two molecules collide with each other. There may be some cases in which three molecules will collide, but this is very rare. So we ignore the effect of this kind of interaction. Therefore, this term, the collision term, is a function of f and f. This is just because we only consider binary collision. So this is a bilinear operator, and you will see how this bilinear operator looks like. Okay, now we put these two terms together. This is a convection, this is a collision, so you get a Boltzmann equation as simple as this. But actually, the right-hand side is not that simple. You look at this formula, you see that this is actually quite complicated. It has a 5-dimensional integral over here, and this looks also complicated, and you have a collision kernel over here. I want to explain it a little bit, because this is what I want to simulate today. Okay, we have two terms. This is in front of this term, you have a plus sign. In front of this term, you get a minus sign. It actually means that you have two particles with velocities v and v1, and they collide with each other. After this collision, you get two new velocities, v prime and v1 prime. So these two are pre-collisional velocities, and these two are post-collisional velocities. And they have a relation like this. But just think of a collision of two particles. Yeah, one with speed 1 and the other with speed -1. If they just collide like this, and then they will just go back with the same speed. Okay, but it's possible that you have a collision angle like 45 degrees, then these two particles may get velocities perpendicular to their original velocities. Okay, this is why we have collision angles here. There are two angles. You can imagine you need to describe a sphere. You need two angles. And also, we have a collision kernel over here, and this collision kernel is dependent on the relative velocity of these two particles. Okay, and you can see that this Boltzmann equation, numerically, this is quite complicated. But actually, this equation is a very classical equation. It was proposed about 150 years ago by Boltzmann, of course. After the birth of this equation, our mathematicians got a lot of things to do. So theoretical mathematicians considers the existence uniqueness of a solution, and applied mathematicians want to simulate this Boltzmann equation. But you can see why this is difficult. Just look at this collision term. A 5-dimensional integral over here. So if you just use numerical quadrature, you need a computational cost like n to the power of 5. So this is already huge. And even worse is that this is just for one v. Okay, v is in this 3-dimensional space. If we want to calculate the right-hand side for one v, you need to do this 5-dimensional integration. So the computational cost is actually something like n to the power of 8, because v itself is already in a 3-dimensional space. And this is just for the right-hand side. You still have another variable x. This will give you another n to the power of 3, so the total computational cost is really huge for this Boltzmann equation. Until now, the simulation of this Boltzmann equation is still a very difficult problem. It's very challenging. Okay, but as you can see, that the most difficult part is just the right-hand side. So temporarily, we will remove this convection term because this is not that difficult. We make the problem a little bit simpler, and we just consider the homogeneous Boltzmann equation, which means that the spatial derivative is 0. The distribution function is independent of the space. Then we get this. So this is simpler because we throw away the variable x, then f is just a function of t and v. Okay, now if you look at this equation, this is a famous result. If you let t go to infinity, then you will get a steady state solution. And this steady state solution looks quite complicated, but it's actually just the Gaussian distribution. This is a function of v, and this is exponential of minus v squared over something, and you get another constant in front of this exponential function. So it's just the Gaussian. You do have some other variables like number density, the velocity, the temperature, or something like this. But in this equation, they can be considered as a constant. Because if you just look at the collision of two particles, it definitely will not change the number of particles. And if you consider the mean velocity, then it's also easy. When two particles collide, it's just some internal interaction, so the mean velocity will not change. For temperature, it's similar. So in our discussion, we just fix these coefficients, n as 1, u as 0, r times t as 1, and then our expression can be much nicer. Okay, now let's look at the current state of the discretization of this collision term. I listed 3 types of method, and you know that what I want to investigate is the last method. But let's look at the first thing, which is a discrete velocity method, which means that for the velocity space, for the variable v, I just use a grid, usually just a uniform grid to do the discretization. Then what does it mean? It means that gas molecules can only take these velocities on the grid points. Okay? I just make this simple assumption, and then our discretization is like this. Fk is just the value of f at these discrete velocities, vk. Okay? After doing this, you can try to find the properties of this discrete velocity method. And what I want to say is that this method throws away a lot of collisions. You have a grid. You say that particles can only take these velocities. Then if two particles collide, it will generate two new velocities. But these two new velocities may not lie on the grid points of this velocity space. If one of these two newly generated velocities is not on the grid point, then we just throw away this collision. We think that this collision doesn't exist. Of course, this This is at most just an approximation. But because of this, you throw away any collision which is not on the grid. It has very good physical properties, like a conservation of mass, momentum, energy, entropy dissipation, positivity of the distribution function, something like this. Okay, but the problem is also very obvious. The computational cost is high, and the numerical convergence order is very low. It's actually, this method is actually lower than first order. So when you do computation, actually, according to my experience, I never see somebody really using this numerical method to do the computation. So this is a much better method, Fourier spectral method. But you know that Fourier spectral method can only handle cases with periodic boundary condition. And in our case, the boundary condition is not periodic. You can see that this is velocity v1. If we don't consider something like relativity, then this v1 is just in the whole three-dimensional Euclidean space. Okay, so because of this, the Fourier spectral method cannot conserve momentum energy, and it doesn't have entropy dissipation. It cannot ensure the positivity of a function. But the computational cost is much lower. I will show this later. And you know that the accuracy is very good. You have spectral accuracy because this is a spectral method. And another method is the method I'm going to introduce today, the Hermite spectral method. I hope most people heard about Hermite polynomials, which is a type of orthogonal polynomials in the three-dimensional space, the whole three-dimensional space. So I use these polynomials as basis functions, but polynomials are increasing at infinity, so I have to suppress this increment using a Maxwellian. Maxwellian is just a Gaussian. So the basis function is actually a polynomial multiplied by a Gaussian. Okay, this page is something very standard. I know a lot of students are learning finite element method this semester. I hope you can understand this page. Okay, this is an expansion of the distribution function. Now what I do is to use the orthogonal property of the polynomials. But here I have a wave function here. Okay, it's slightly different from the local linear functions or something like this. Okay, now I make a definition. I let psi to be the product of h and m. What I want to do is just to combine this and this so that I can just use this as basis function. So this expansion is exactly the same as this one. Okay, then what you want to do is to find the expansion of the right-hand side, which is a collision term, QFF. For the right-hand side, I also want to expand it into the same series, the similar series, but just with different coefficients. Okay, but here you can see that QFF is a bilinear operator. Therefore, in its expansion, the coefficients should also be a bilinear function of the coefficients for f. And then, yeah, but this is a very abstract form. You know that you should have some coefficients here. Now what you need to use is just the orthogonality of the basis functions, and you can find the coefficients in this expansion. So until now, everything is very standard. It's completely classical. And eventually, what you get is just an ordinary differential system for all these coefficients. Okay? As you can see that this is just to apply the classical Hermite spectral method to a very classical equation, Boltzmann equation. And then the result is just like this. Okay, this is almost everything about our algorithm. You can see that it seems to be a little bit strange. So this is too simple. So you just apply a classical method to a classical equation. It should have been done many, many years ago. So why are we still doing research in this direction? So actually, this is really not a new idea. This idea was first introduced many, many years ago, about 70 years ago as moment method. But now, this method was not popularized because of its low efficiency. I will show you these two parts. Okay, for numerical method, the most important thing, two things. One is the computational cost. The other is the order of convergence. We just, yeah, for this one, you know that this is spectral method, so the order of convergence shouldn't be a great problem because we guess it has spectral accuracy. It should be good. But what about the computational cost? Okay, you look at this right-hand side. You have 9 indices for these coefficients A, I1, I2, I3, J1, J2, J3, K1, K2, K3. So you can imagine that the computational cost of this right-hand side is O, m to the power of 9. Here I have an m here because I need to do truncation, just like all the spectral method. I need to do truncation, I truncate at m, so the computational cost is like this. Okay, now I want to compare this computational cost with the computational cost of other methods. For example, if I don't do anything, I just apply a direct discretization. As I told you, the computational cost is like O(n) to the power of 8. And we introduced 2 other methods. The first one is a discrete velocity method. I can tell you that the computational cost is like n to the power of 6 plus delta, with delta less than 1. Okay, and another one, Fourier spectral method. This is even better because the collision operator has some convolutional structure. So the computational cost is like O(n) to the 6. But this is in a general case. Maybe somebody know that there are some special cases where you can further reduce this computational cost. But in general, it's like this. If you look at all these methods, you can find that the computational cost is always lower than this. This has a power of 9 here. Then why do we still want to use this method? This is what I want to introduce in the following part of my presentation. But what you can see is that maybe we don't want to use this method, although it's not very expensive. But the convergence order, as I said, is very low. It's lower than first order. So we don't want to use this method. But this method apparently is a very good method. So what's the reason for us to study a method as expensive as this? Yeah, because this is a Hermite spectral method. You can consider this as a mesh-free method. Each direction you use m basis functions. But here, these methods are grid-based methods. So I used another notation. Okay, yeah, this is another possible choice. Even if I say that I want to use spectral method in a whole space, I do have a better choice. You know that in a 3-dimensional space, okay, how can we construct orthogonal basis functions? One way is we use the Cartesian coordinates. So in each direction, you have a set of orthogonal polynomials, and then we multiply these orthogonal polynomials in the 3 dimensions together, and you get a set of orthogonal polynomials in the 3-dimensional space. But another method is that I can use spherical coordinates. I first construct orthogonal polynomials in the radial direction, and then I construct another set of orthogonal polynomials on the sphere, and then you multiply these 2 together, you can also get a set of orthogonal polynomials. This is the idea of using spherical coordinates. You can see that here I have something like Laguerre polynomials, spherical harmonics. I don't want to introduce the details. I just want to say that if you use these basis functions, you can get a very similar expansion. And then you get a very similar expansion of the right-hand side. And then you also have something like ordinary differential equations for this system. Okay. But now, if you look at these coefficients, so this is actually the new collision kernel under these new basis functions. You have a delta here. Because of this delta, although there are 9 indices, you can reduce the computational cost by 1. So the final computational cost is O(m) to the power of 8. Okay, this is also lower. This computational cost is also lower than this. Then this is a question. Why do we want to consider the Cartesian-based Hermite spectral method? Okay, until now we need to answer 2 questions. The first one is, why don't we use this Fourier spectral method? And the second one is, why don't we use these basis functions? Okay. To answer these questions, I need to drag you a little bit far away from this topic. Before we can, yeah, you know, now the computer flops are actually very large. So every second you can do a lot of maybe 10 to the 9 floating operations. But before this area, before this period, before our computers are so strong, what people did was something like this. Okay, I have a very complicated collision operator. I cannot simulate it, so I replace this by some simple ones. These are some simple ones. This is called BGK model. This is called Sharkov model. What do? This is the original Boltzmann equation. We know that this right-hand side is complicated. But we know a very special property of this right-hand side, which is that when t goes to infinity, we have a steady state. The steady state is this Maxwellian. It's a Gaussian. Okay, then I want to replace this right-hand side by a new right-hand side. And I want to ensure that this new right-hand side has the same property. This is not difficult to find that. It's not difficult to find that if you consider this coefficient as a constant. It is a constant in this case. If you consider this as a constant, then as t go to infinity, if you replace this q by this q, then f will be this Maxwellian, because this Maxwellian is just here. And this model is very well known. It's known as a BGK model, and you just need to choose a coefficient appropriately. You can simulate, you can recover most properties of the fluids. But there's one property which cannot be recovered by this model, which is heat conductivity. So this is just like a coefficient in front of a Laplacian in your heat equation, heat conductivity. Okay, so we need another model to fix this property, and Sharkov did something like this. He multiplied this Maxwellian by a cubic polynomial. I will not say too much about this cubic polynomial, but by doing this, we can get correct heat conductivity when the fluid is close to the equilibrium. Okay, by doing this, we get some new models, and people used these new models to do simulations. And for these new models, the computational cost is much lower. But what are they really doing? This is another page of formulas. I will explain it line by line. Okay, so the first line, our expansion of the distribution function, I introduced it just now. This is a basis function. Okay, so what we want to try is to expand these new models, not really new, but here we consider these as a replacement of the original collision term. If we do this expansion, we see that the result is roughly like this. So you also get the product of two f's. You'd also get some coefficients, so it should be very similar to the original collision model. However, if you look at these coefficients can be considered as a matrix, because you have one set of indices J1, J2, J3, and the other set of indices K1, K2, K3, so they look like a matrix. Okay, and these coefficients, for most cases, these coefficients satisfy this condition. It means that in most cases, this matrix, for most places, this matrix is just a diagonal matrix because of these deltas. It's just a diagonal matrix. But when these J1, J2, J3, and K1, K2, K3, these indices are really small, you can find that these coefficients are actually the same as the coefficients in our expansion of the original binary collision operator. So what do I mean? Okay, for these new models, we have one expansion. For our original collision term, we have another expansion. You can see that for most cases, this will not match this. But when these coefficients, when these indices are very, very small, they do match with each other. So in this sense, we can consider these two models as approximation of the original collision term. Okay, but now we have a much better way to do this, because now the computational resource is much better, so we can really figure out a lot of coefficients like this. So we just mimic this idea and do something on this page. The first step, we just do this expansion. Okay, we want to calculate all these coefficients, not all because the number is infinity, but we can calculate a lot of coefficients for these coefficients A. And then what we want to do is something similar to the BGK and Sharkov models. We match the first few coefficients. we find an index set I, and say that if these indices are small, or these indices are in this index set I define this A tilde as the same one as these A's. Okay. In other cases, I just set this just like this. I set this matrix as a diagonal matrix. Okay. Then we get a new collision model. For this, as I said, for this new collision model, for most coefficients, it will not match the expansion of the original collision operator. But for the first few ones, especially for indices in this index set, I will match these coefficients. So this is the basic idea of our algorithm. And by doing this, you can see that the total computational cost is much lower. I have a small set of indices, and for this part, it's expensive. You have m0 to the power of 9 here. But for most coefficients, it's because the matrix is diagonal, so the computational cost is just m to the 3. And this 3 is because it's a 3-dimensional problem. Okay. And now I want to answer the question why we want to use Hermite spectral method instead of a Fourier spectral method. There are some deeper reasons. In our expansion, you see that we have some coefficients Fij, k. And actually, these coefficients have very clear physical meanings. For example, the first coefficient is just a density, and if the sum is 2, you get stress tensor. If the sum is 3, you get heat fluxes, so on and so forth. So these coefficients are really the important ones. So why do we want to solve Boltzmann equation? It's not because we want to figure out the distribution function of the fluid. What we really want to get is just some basic fluid properties like density, velocity, temperature, so on and so forth. So these few coefficients, the first few coefficients are actually the most important ones in our simulation. Okay, and the second thing I want to mention a special type of molecules proposed by Maxwell as approximations of the real gas molecules. For this special type of molecules, if you look at these coefficients, it has a special property. These coefficients are equal to 0 if I1 plus I2 plus I3 plus, anyway, the sum of these 6 coefficients indices is not equal to the sum of these 3 indices. In this case, the coefficients are zeros. What does it mean? I will switch to the next page. This is our original ordinary differential system. Okay, and as I said that if this is not equal to this, then all these coefficients are zeros. Then what can you conclude? You can actually remove some of these coefficients from this right-hand side. Some terms, actually many terms on the right-hand side. Okay, you see that if I1 plus I2 plus I3 is less than or equal to K1 plus K2 plus K3, then because all these coefficients must be positive, if this is violated, I mean that the left-hand side is greater than right-hand side, then this plus this cannot be equal to this. So the coefficients are zeros. Similarly, for this one, if J1 plus J2 plus J3 is greater than K1 plus K2 plus K3, then because these coefficients must be positive, so you must have this inequality. And in this case, if this condition is violated, then all the coefficients are also zeros. So all these terms can be thrown away because they are just zeros. So now if you look at this right-hand side, this is much better. This is because once you fix the K1, K2, K3 on the left-hand side, this right-hand side is just a finite sum. Originally, this is an infinite sum. The indices are from 0 to infinity, and now you just get a finite sum. And this is much better. And the even better thing is that if you consider a set of coefficients for which the sum of the indices is smaller than less than or equal to m0, a given number, then all these coefficients will form a closed system. This is a very special property for these special molecules. In general, if you do a discretization of a partial differential equation, all the degrees of freedoms are coupled with each other. This is a normal case. But in this case, you can find that if you just pick the coefficients in this set, And then these coefficients will be automatically closed. You don't need to do something like moment closure. The system is automatically closed, which means that if you just solve the equations, ordinary differential equations for these coefficients, you get exact results. So this is what I say here. This right-hand side gives exact evolution for the coefficients with indices in this index set. Okay, it also means that this infinite ordinary differential system is reducible. But this is just for a special type of molecule, Maxwell molecules, an approximation proposed by Maxwell. In other cases, it's not like this. All the degrees of freedoms are coupled with each other, but those kind of coupling is relatively weak. So this is from our numerical experience. We see that if we consider coefficients satisfying this condition, and these coefficients are usually very small when we consider realistic collision kernels. Therefore, in our simulation, M0 can be much smaller than M, and then because you see that the computational cost is like this. This is the expensive part. This is the less expensive part. And if we can choose M0 much smaller than M, then the computational cost can be controlled. And I want to say that this computational can be controlled to be even less than the Fourier spectral method. Okay, and also you know that if you just need to consider a very small M0, which means that the quadratic part or the binary part of a collision kernel is just restricted to the first few coefficients, then you can still get very accurate density, stress tensor, heat flux, velocity, temperature, all kinds of things we are really interested in. Okay, the last thing I want to mention is that the same idea cannot be applied to the discrete velocity method or Fourier spectral method. For these methods, all the degrees of freedoms are coupled with each other very strongly, and we cannot do this simplification. Okay, and here I have already answered one question, why we use this new method instead of the cheaper Fourier spectral method. And there's another question to answer, which is the comparison of these two basis functions. And as I said that in this expansion, you get a delta here. Therefore, the computational cost of this should be one order lower than the computational cost of this. But currently, we are still using this. And this is mainly because the computation of these coefficients is extremely difficult. And it's also very expensive. We don't have a very straightforward way to find these coefficients. So first, you can see that the number of these coefficients is O(n) to the 9. And for each coefficient, if you want to find the value, then you need to do a lot of numerical integrations. So this is too expensive. But for these coefficients, it's much easier. We have explicit formulas for these coefficients. What I want to mention is that actually this is really better, because you can see there is a delta here, so the computational cost of this is really smaller than this. But as we said, the coefficients are difficult to obtain, but we do have another way to obtain these coefficients. To obtain these coefficients, you can first find these coefficients, and then by some transform, and then you get these coefficients. And the reason is that it's very simple. It's just a linear operator, and I have two different bases. And these bases can be represented by each other. So using a linear transform, you can always convert one coefficient to another. OK, but this conversion has this huge computational cost. It doesn't matter because we only want to compute these coefficients once. But this also takes several days in a workstation. OK, as I said, for these coefficients, I have explicit formulas. I don't want to really mention these formulas. It's pretty complicated. You can see that it involves a lot of other manually introduced quantities until here. Okay, and what I want to mention is just here. The computational cost is OM0 to the power of 12. So this is also very expensive. But as I said, we just need to do this once. And then it can be applied to all the computations. And another thing I want to mention is what I mentioned in the title. I claimed that I am solving the non-cutoff Boltzmann equation. So what does it mean? what we are considering is something called the inverse power law model, and it means that the force between two molecules is proportional to the inverse power of the distance between them. So this is so if two molecules collide with each other, the trajectory is roughly like this. Okay, and this kernel has a property. If you integrate this kernel, you get infinity. So this is just like in some non-local problems, you have non-integrable kernel, and this is the same case. But actually, this introduces great difficulty in both analysis and computation. So what Grad proposed is Grad's cutoff. So he changed this original collision kernel to a new collision kernel, such that for this new collision kernel, it's integrable. So of course, this simplifies the problem a lot. By doing this, we can use the SMC method. It's actually a stochastic method because you know that this is a 6-dimensional problem. For high-dimensional problems, we use Monte Carlo method. So this is one type of method. And for Fourier spectral method, I think it's possible to do this non-cutoff Boltzmann equation. But currently in the literature, I never see anybody using this to do the computation. And I tried to do the computation by myself, but I found that finding these coefficients, the collision kernels of this inverse power law model is very, very expensive. So I think this is also one of the reasons why people don't consider this. Okay, so the following simulation is possibly the first simulation of a non-cutoff Boltzmann equation. Now I just want to show the numerical results very quickly. So for the Maxwell gas, the special kernel I mentioned just now, it has an exact solution. Okay, this is just the approximation of the initial condition. You can see that if we use spectral method, I just need to use m equal to 20. I get very good approximations. Because this is a 3-dimensional function, it's very difficult to plot. So I integrate 2 dimensions out, and I get a 1-dimensional distribution function, marginal distribution function. And you can see that our approximation matches the exact solution very well. But this is just the initial condition. When time evolves, then you can see that we still get very good approximation. Here, m naught is just chosen as 5 or 10. For 5, maybe you can still identify some difference, but for m naught equal to 10, it's almost identical. Okay, this is the evolution of some moments. I just want to show that it matches the exact solution very well. This is the information. Okay, second numerical example. This doesn't have any exact solution, but I would just want to show that I use different m naught to do the simulation. It converges very quickly. And yeah, this also shows very good convergence for the interesting stress tensor. This is another example with discontinuous initial distribution function. In the discontinuous case, if we want to for discontinuous function, if we want to approximate this function using spectral method, usually the quality is very bad. In this example, the quality is really very bad, so I don't show this. But what I show here is just the evolution of some moments. For example, heat flux, the stress tensor, or something like this. But for these quantities, you can see that the convergence is still very good. Okay, now we add the spatial variable x. But we just solve the steady state, so we remove the time derivative. There are some numerical strategies like the HAL numerical flux. This is something very simple. And we use linear reconstruction to get second order. We use multi-grid iterative solver to get to steady state much more quickly. And the test problem is a quiet flow. So this is also a very simple one. So you assume that the gas is between 2 parallel plates, and you drag this plate downward, you drag this plate upward, and then because of a friction, the gas inside between these 2 plates will move and eventually form some steady state structure. And here, these are parameters. But the only thing I want to say is this Knudsen number is 0.5. It means that this gas is very rarefied. So it means that if I have a molecule here and it flies perpendicularly to the other plate, then this molecule will collide with other molecules only twice. So you can imagine that this is a very rarefied gas. And these are the numerical results. Actually, I have been doing this numerical example for a lot of years, and the first line is the best numerical result before this work. So I did this for many, many years, and I can match density very well, I can match velocity very well, but for temperature, these dots are from Monte Carlo results, and this straight line, and sorry, this curve is my result. You can always see some difference over here. And now I use this method, I get much better matching. Okay, I think the time for me is already up. So I just want to leave a summary and our future work here, and thank you for your attention. What I want to say is that for almost all examples, if the gas is really rarefied, for example, in this case, you see that Knudsen number is 0.5. So this number, when this number is larger, then the gas is more rarefied. If this number is greater than something like 0.1, BGK always has significant difference between the real results. So BGK, for rarefied gas, BGK is not quite reliable, and this is why we want to consider the original binary correlation.
But the LBM method is based on BGK.
Yes, so this is why LBM can only consider some gas relatively dense or some incompressible fluid. You can imagine that when something is incompressible, it must be very dense. I'm sorry, it's what?
It's faster, it's bigger than this. The velocity is bigger.
So in this example, it's very strange. The velocity doesn't affect the result very much. You will change, yeah, when the velocity is larger, you will change this velocity. And we also change this temperature, but it will not make our result worse. So maybe if you increase this Knudsen number, we need to have a larger M naught to get better results. But the velocity is fine. It doesn't have a lot of affection.
So what's the reason of the temperature, the linear, the next slide? The temperature is not good enough for the linear isotope. Why? What's the reason?
So the nonlinear model is better. This is just because the original Boltzmann equation is nonlinear. And this linearized model means that we first linearize the original Boltzmann equation. So in this step, we have already done an approximation. But this approximation makes the computation much easier, but it also makes the numerical result a little bit worse.
But density and velocity is good enough.
Yes. So we cannot really explain this, but what we can identify is that, okay, this is not as good as this.